Bonsoir, je m'appelle Bartosz Golaszewski, je vais parler de GPIO et je vais faire ma présentation en anglais, mais n'hésitez pas de me poser des questions en français après. So, welcome to my talk. I'm going to be talking about a concept that is familiar to everyone that works in the field of embedded Linux and IoT in general, but that is surprisingly tricky to get right programmatically. And the thing I'm talking about is the general purpose input-output. So I work for Baylibre. We are an embedded Linux consultancy based in Villeneuve-Loubet here in southern France. For most part, we help clients launch IoT and embedded Linux and Android products from concept through prototyping, through design, up to manufacturing. We also work closely with the open source community. We upstream Linux kernel support for hardware platforms. We do a lot of maintenance for various open source projects. And we're also the founding developers of kernelci.org, which is now is the official endorsed by the Linux Foundation continuous integration loop for Linux kernel. And I personally have been in the field for 10 years now. I work both in the kernel and user space and also in various Linux-related build tools. And I maintain the GPIO subsystem in the kernel, and also I authored and maintain Lib Gpiod, which is the user space part of the GPIO stack in Linux. So the agenda for today is this. First, I'm going to be talking about what GPIOs are, just a brief summary. Then we'll dive deep into the kernel to see how the kernel handles general purpose input-output. Then we'll see how you can interact with GPIOs from user space. And finally, we're going to reach the upper layer of the stack, which is Lib Gpiod, the official library for GPIOs in Linux. What it is, what it does better. I'm going to show some examples and talk about the bindings and what's coming next. So as I said, GPIO stands for General Purpose Input-Output, and conceptually it's just a pin, a bidirectional pin that can be configured to be in input mode when we read its value and in output mode when we drive the value. It can be as well enabled, disabled, and be a source of interrupts. And GPIOs are provided by either SoCs or various expanders and MFD multifunction devices. And what can we use them for? There are a lot of applications, and they are literally everywhere. But just to give you an example, you can have a device like an EEPROM chip that talks to the SoC over I2C, but it has a write protect pin, so it will expose this pin to the system, and then if the system drives it high, we enable the write protection of the EEPROM. Or you can have a temperature sensor that when it reaches a programmed limit, it raises an interrupt on a GPIO pin that it exposes. So what happens in the kernel? In the kernel, we have a provider-consumer model where expanders and SOCs expose GPIO lines to consumers, which are various drivers that simply use GPIOs either in input or output mode. And right now we have two coexisting interfaces. So one is a legacy. I'm not going to go into detail here. It's based on a global GPIO number space, and it's largely deprecated. It's no longer allowed to be used in drivers, and it's soon to be phased out as soon as we can get user space to stop using it. And the second interface is the one based on GPIO descriptors. So this, to give you an idea how it works, drivers that expose GPIOs and drivers that use them are connected using interfaces such as ACPI or device tree, so that the drivers only see, the users only see the GPIOs that they are using. This allows for a much more fine-grained control over GPIOs. Just for accounting, the provider drivers are mostly in the kernel source in drivers/GPIO, and the consumers are all over the place. And the idea is to provide the drivers with a straightforward API so that users write kernel drivers that deal with GPIO. So it's highly discouraged to use them from the user space. but sometimes it's necessary or preferable. So when do you want to use GPIOs from user space? For many, there are certain types of devices for which there are no correct kernel subsystem. So for instance, power switches, relays, devices such as GPS and Bluetooth devices often expose GPIOs that are controlled by dedicated software from user space. And also certain users prefer to toggle GPIOs from user space. Mostly I'm talking about intelligent home systems, robotics, and also during the prototyping phase for many products, makers just write Python scripts that toggle GPIOs. And we at the Linux kernel mailing list are trying to make it not easier, I wouldn't say, but at least make it correct and robust. So the standard interface that has been historically used a lot for GPIOs is the Csfs interface. How many of you have used Csfs for GPIOs? Yes, so there are some. So this is an interface that comes with many problems. It has been merged erroneously to an extent when the GPIO subsystem had no active maintainer and it just got merged with a slew of other things. The problems that come with this interface is that the state of GPIOs is not tied to any process. The process can access GPIOs concurrently, and none in the user space can really take control over a GPIO line. Also, the process crashes and it has changed certain settings. The GPIOs will remain as is, as they were at the time when the process crashed. And also the interface, the programmatic interface is quite cumbersome. So we have several attribute files in the Csfs for each GPIO line, like value, direction, active, low. The lines are exposed using the global GPIO number space, which requires users to calculate the number of the GPIO they want to expose. These numbers are not stable. If you have dynamic GPIO expanders, these numbers can change. And also polling for interrupts is possible, but very complicated because you need to always reopen the value file when there is an event, and it's because of the overhead and the fact that the events are not queued, you can very easily lose them. So it's not robust enough to implement, for instance, bit banging protocols in user space. So to address these issues, we have developed a new API for the GPIO subsystem in user space. It's called the character device because it's a single character device called def/GPIO chip 01 and so on per GPIO chip. So as you can see now, instead of what we did with a flat representation of what is basically a two-level hierarchy, we were actually representing it as such. Every chip exposes a set of GPIO lines, and a chip can be operated on using standard Linux interfaces. So system calls, open, ioctl, poll, read, and close. There are many new features that the character device implements. So we can request multiple lines at once. We can actually take control over GPIO lines with a single process, so that another process can no longer use these lines. We can look up GPIO lines by name, same with chips. We can set various drive flags like open source, open drain. We can mark the GPIO lines that we use with a consumer string so that the system, other users in the system know who's using them. And finally, we have reliable polling for interrupts. However, even with the new API, we've not been able to get it right this time, but it's not a problem because we always plan to throw the first one away. The problem with kernel APIs is that once it's released, it's there. You can no longer change it or remove it. It has to remain stable. So we developed another interface. This time, it's hopefully gonna be the right one. This has been merged recently in Linux 5.10. So the problems that people raised with the previous API, the previous interface, was that it was no longer possible to add new settings because users have started asking for, can we configure the debouncing from user space? Can we change the interrupt timestamp clock from monotonic to real time? Can we set the bias flags? Can we get the sequence numbers for interrupts because we want to implement some protocols that rely on strict sequencing? So all this has been implemented in the version 2 of the character device, and now it's available. And so how does it work programmatically? The character device defines are in the Linux kernel source, in the Linux headers under linux/gpio.h. They are conceptually split into several sections, like chip information, line information, requesting lines, reading line values, and eventually polling for requests, polling for events, and reading information about them. And the top level of the stack that is built on top of the kernel API is Lib Gpiod. This is a C library and a set of tools and higher level language bindings for interacting with the character device. The history behind it is that somewhere in 2016, we needed a way to elegantly toggle power switches on a Baylibre Acme device, which is a power consumption measurement device that we developed a while ago. And I tried the industrial input-output attributes in Linux, but this idea was shut down by the maintainers. I tried to implement a way to control Linux regulators from user space, but also the Linux maintainer for the regulators declined the patches. And finally, I decided to use the GPIO character device, which was under development back then. After a couple weeks of development, the first version was released in 2017. Next year, around the same time, the first stable version was released, and the current stable version is 1.6.3, so this is the one you should be using if you decide to go with it. And version 2 is coming soon. This is the version that we will release that will support the second version of the kernel interface. So what's inside? The package contains a C library, which is the low-level interface, fully documented. All symbols are fully documented in Doxygen. It contains a couple command line tools to replace shell scripts writing to Csfs attributes. It contains a custom test suite that we use together with a kernel module called GPIO Mockup, which exposes dummy GPIO chips, and we use it to both test the library and the kernel interface and the kernel, like the in-kernel interface for GPIOs. And we also offer C++ bindings and Python 3 bindings for easier for writing in higher level languages than C, which is not really preferred for most people. So just to give you an idea how the GPIOD tools work. So we have several programs. GPIO Detect just lists the GPIO chips that are present in the system. GPIO Info additionally shows information about lines, so we know that we have this and this number of lines. The lines have labels. They are either used or not used, and we also show their flags. Next, we can look up GPIO lines by their names, which the program simply returns us the name of the chip and the hardware offset of the line under given name. We can set GPIO values, we can read current values of the lines, and we can also monitor lines for events, which is shown below. When simply an event is triggered, we display information about it. We also implemented C++ bindings, which simply wraps the C API and C++ in modern C++ classes to allow users to fully profit from C++ features. Everything is as well documented in Doxygen, everything is exception safe, and the tools are re-implemented in C++ to show some examples of how to use the interface. Something that is by far the most popular feature are the Python bindings. I just see from the amount of mail I'm getting about this part that many makers and people who prototype products use Python to interact with GPIOs. So again, the entire C API is wrapped in a set of Python classes. Everything is fully documented, and technically the code is written in C, but it simply uses the Python 3 extensions to expose a Python module seamlessly. As well as with the C++, we have all the tools re-implemented in Python to show some examples of how to use the interface. So a thing that is coming soon is the dbus interface. So dbus is just a standard protocol for inter-process communication in Linux. And one of the issues raised by many users of Lib Gpiod is that they can no longer have a central authority for controlling GPIO lines like the sysfs was. So the GPIO dbus daemon will run in the background as this central authority, and users will simply use dbus messages to query GPIOs and then subscribe for events and do everything that the C API allows. So the version 2, as I said, is being currently developed. If you go to the Linux GPIO mailing list, you're going to see that we're currently working hard at bringing you the version 2 of Lib Gpiod. The C API has been entirely reworked to support all the features exposed by the by the most recent kernel interface. We have decoupled the chip and line requests so that chips and requested lines can live separately. This was a feature that was called for a lot. We have entirely reworked language bindings, and we're also going to offer Rust and glib bindings when it's released. So where to get it? It's hosted at kernel.org. I posted the links to the Git repository and the website that contains all the releases. I maintain the recipes in Meta Open Embedded and Buildroot, and I know that others have packaged the project in Fedora, Arch, and several other popular distributions. And the discussion and development happens on the Linux GPIO mailing list. If you send any questions or patches to the list, just prefix the subject with Lib Gpiod. And that's it. Thank you very much. So I'm taking questions also in French.
Thank you for the presentation. I would like to know if both systems, the C1 and the new one, can coexist in the same platform with the same kernel, so that legacy programs can profit from the old API, and new, brand new programs can use your implementation.
Yes, very much. Both are. They can coexist. They can be compiled in at the same time and used at the same time. By default, the sysfs is now disabled in any kernel that you compile, like the default value. But you can enable it if you really want to. Soon, we'll probably start throwing warnings in the kernel log if you're going to be using them. But yeah, technically, they can still coexist.
D'autres questions? N'hésitez pas. Sinon, ce sera l'occasion de vous rencontrer. Je vais reprendre juste quelques mots quand même. Encore merci, félicitations. Moi, voilà, les GPIO sous Linux, je dis bonjour aux copains de la robotique. On en a connu, on a fait du RT Linux, du ROS et tout ça. Donc on avait très à cœur de te recevoir ce soir, et puis aussi de pouvoir parler de Baylibre, une belle initiative dans l'électronique et l'open source, dans la plus belle région de France. Donc c'est toujours un plaisir de vous rencontrer, d'échanger avec vous. Encore merci et bonne continuation, et j'espère qu'on organisera très très vite un atelier sur les GPIO sous Linux, remettre les mains dedans, montrer à tout le monde, et bravo pour les progrès qui ont été faits et le maintien de cette libre open source. Merci beaucoup, encore bravo.